Hi everyone. Today we will be diving into the transformative world of automation, a journey where machines, algorithms, and artificial intelligence are not just tools, but our partners in progress. Imagine a world where mundane, repetitive tasks are seamlessly executed by robots, freeing up human potential for innovation and creativity. From the assembly lines of automotive giants to the intricate processes in pharmaceutical labs, automation is revolutionizing industries, making them more efficient, accurate, and cost-effective. Let's look at healthcare for a second. Healthcare is an area where automation in diagnostics and patient care is saving lives by reducing human error and ensuring timely interventions. Or take manufacturing, for example, where assembly lines have been transformed by automation. Automated systems now handle precise and repetitive tasks with unmatched efficiency, from welding car parts to packaging goods. The speed at which these machines can complete tasks is unmatched by the human workers. This not only speeds up production, but also maintains a high level of quality and consistency, allowing human workers to focus on oversight, innovation, and tackling complex problems that require creativity and critical thinking. Taking a step back from the manufacturing process, we can also look at farming. Automated farming is another remarkable application. With the help of GPS-guided tractors and harvesters, automated irrigation systems, and drones for monitoring crop health, farmers are now able to optimize their yields while conserving resources. Automation in agriculture ensures that we can meet the food demands of a growing global population efficiently and sustainably. It reduces labor costs, increases productivity, and makes farming operations more predictable and manageable. However, this shift towards automation is not just about replacing human effort with machine precision. It's about creating the most efficient environment possible where humans and machines collaborate, enhancing each other's capabilities. It's about unleashing our potential to tackle complex problems and explore new frontiers. Through this video, we'll explore a little deeper into the landscape of automation. To bring this concept to life, we'll delve into an exciting project involving a small Jetbot that can follow lines on a road. This project will demonstrate how automation can be applied in real-world scenarios, highlighting the principles of machine learning, sensor integration, and control systems. By building and programming this Jetbot, we'll witness firsthand how autonomous systems can navigate, adapt, and perform tasks with precision and efficiency.
Thanks, Nick. Let's take a detailed look at the central elements of this Jetbot process and how they enable a system to function effectively. At the heart of the system is the live image display to the computer. This element is critical because it serves as the interface between the robot's camera and the operator or processing unit. The camera continuously streams real live visuals, allowing for dynamic monitoring of the robot environment. Without this visual feedback, the robot would be essentially blind, unable to adjust to the changing surroundings. Next step is identifying the centerline and angle detection. This is where the system analyzes the live image feed to identify the centerline in the robot's field of view. This step uses advanced image processing techniques such as edge detection and line tracing to locate the path the robot must follow. Additionally, the angle between the robot's current direction and centerline is calculated. This data forms the foundation for the robot's path correlation logic. After identifying the centerline and angle, the system performs coordinate analysis. This converts the visual data into a precise positional coordinates, allowing the robot to determine where it is in relation to the centerline and other objects in its environment. Next, the system can command the robot to do a 360-degree spin. This is a feature to signify the start of the running portion of our demonstration. For this movement, precise kinematic control is required, which operates a single motor for a specified 1.09 seconds, just enough time for the robot to spin once and recapture the centerline in its field of view. Live location reporting is another key feature for this Jetbot. After it's finished its initiation turn, it provides an update of its location using a third-person view from an overhead camera, and reports back to the operator in our system. This feature allows for a starting point of the robot to be established and could be used in a number of applications beyond the scope of our demonstration. The next critical step is Jetbot following the line. Once the centerline and angle are identified, the robot uses this information to dynamically adjust its trajectory, and this process involves continually recalculating correlations for each motor to maintain alignment on the centerline. The robot follows the line smoothly, even if the path curves or the environmental factors change, as you can see here. But what happens if the Jetbot reaches an intersection or the centerline disappears? That's where we can terminate the robot motion. It comes into play as the centerline might end or the system detects an intersection. The Jetbot halts its movement. This is a safety feature, preventing the Jetbot from continuing blindly into potentially undesired or dangerous areas.
In the first 3 labs, we learned a lot of different things about the Jetbot and different ways to control it, including kinematics of the Jetbot, sign recognition using deep learning, path following using image processing, position detection using the April tag and a above camera. We also use that camera for path planning of the Jetbot. With that being said, we had to pick what we wanted to use for our final demo. We settled on using kinematics and path following using image processing. We also added some position detection using the April tag to show where the Jetbot started from. After deciding which techniques we wanted to use, we had to work through some kinks and figure out how we were going to combine these codes to work together. That obviously took some time, but we all worked together and brainstormed different ways to do things. For example, one of the ways we thought of making our code easier to work with was to change the limits on the sliders to just the max and minimum being the value we wanted it to be. That way we could have the value just automatically set to where we wanted it to. We didn't have to reset the slider every time we wanted to go through and test our robot. Following that, we have some video clips here of us working through our different techniques. First, we have our test of kinematics, making sure that was working fine, followed by line following using image processing. And as you can see, here's our robot following the line in the roundabout. And finally, we were able to put all this together for our final demo. So here we have our robot spinning in a circle to showcase the use of kinematics. Then it is reading its position via the above camera and the April tag. And then it is following the path using image processing until it reaches the end of the line.